All right, everybody, on to the next section of material. This one is about the chain rule. Whenever we look at the chain rule, we have to think about something that's called a composite function. So this is probably like maybe a new topic for a lot of you. Composite functions. Okay, so I'm hoping that the word composite isn't brand new to a lot of you. Composite normally means like you can have composite wood or something like that. So if you're in music, you can have a composite. Um, oh my gosh, I can't think of the word right now. Composite music basically, where you put the harmony on top of the I can't think of what that's called, but anyway, sorry about that, my brain froze on me. But there's you may have heard that word composite. If you haven't, then the idea here, let me give you a little definition first. It is one function that has a function inside of a function. Okay. So we're gonna compose. That's what I was thinking for music compositions. Okay, we're gonna compose something by sticking stuff together, basically. Okay, so you're gonna have an f of x or a g of x or whatever it is, an original function, but it's going to look like some function inside of another function. Okay, so in your book, it looks like this. Here are some examples. Y equals the square root of 4 minus x squared. Okay. And so my question is, can you see that this is indeed one function, the y equals, that's composed of two different functions put together? Okay. I hope you can, but just to make sure, let's go ahead and see it. Okay. So here I've got this guy, the square root function. Okay. That's a function we've worked with before. We did the little flower power thing to change your exponents around and stuff like that if you needed to change your exponents, right? Okay, so this, I consider this the outside function. Okay, literally because it is on the outside. Okay, it's kind of like the bracket that's enclosing the other function. And then on the inside, we have this guy going on, 4 minus x squared. That is also a function, right? And he is on the inside of the bracket. He's the inside function. Okay, so you literally have one function, 4 minus x squared, who is inside of the other function, which is square root. Okay, so you're gonna have to be able to like kind of pull those apart and look and see, do I think that's a composite function? Do I, don't I? I'm not sure. Let's look at it. Okay, so here's you another example. Take a second and see if you think you can figure out, is it composite? Maybe it's not. Maybe I'm just fibbing to you or something. Okay. If it is composite, then find the outside function and find the inside function. Okay, so hopefully that's long enough for you to decide, is this a composite function? One function y that's made up of two different functions. I think it is. I see the cubed root function. Let me do my covering up method. Okay. So that's a cubed root function. And if it was just the cubed root of x, we would be done, right? Like we would say, hey, let's use our flower power and say x to the 1/3. Okay. Rearrange that so that we've got a fraction exponent and we would be done. As excuse me, x to the 1/3 is totally a power function, and we can totally take the derivative of that using our power rule, right? Okay, so that's a function I can take a derivative of. And then inside here, I've got x squared minus 1. Well, is that a function? Yes. Okay, that's also a pretty polynomial function, right? And whenever I look at that, hey, I could use the power rule to take the derivative of that guy, right? The problem comes in whenever they're stacked inside of each other like this, okay? So first of all, yes, this is a composite, okay? And then second of all, the problem is being able to do something with it, okay? So, like, last time whenever we did the power rules, if you had something, let me show you a separate example. Let me let me make sure I can prompt you here. If we had just the cubed root of x, like I said, that would be x to the 1/3, right? Remember, your power is up here. That's the top. That's the petals in the flower. Okay. And the root is the index number here. And on a flower, that would go on the bottom, right? So it's the power on top, the root on bottom. That's your flower power. If you don't remember that, I think I drew a picture and everything. Okay, a pretty little picture, right? So flower power. The power is in the petals. The power is on top. The root goes on bottom. Okay, so anyway, you should be able to, hopefully you got those exponent rules really strong right now, and you should be able to rearrange that. And then you would just say, hey, look, y prime is just what? Power rule, right? Take the 1/3 out in front, write the x, subtract 1 off of here. Be careful because it's 1/3 minus 1, so this is going to be a negative 2/3. And you can move that to the bottom if you wanted to, but I'm happy. Okay. The problem is that I've got other stuff inside of here. Inside of that, it's not just x, it's x squared minus 1, right? And so doing this right here, it's a start, but it doesn't address the fact that I've got this inside guy going on. Okay. So that's what we're going to work on today is what the heck, if it was just X, we'd probably be okay. But what do I do whenever it's some more advanced function inside of here? And these are the ones, these composite functions, these are the ones that bug people. Okay. So I'm not trying to say you should be bugged. Don't freak yourself out here. Okay. I'm just saying your normal rules that we've been working on for the last couple of weeks are not going to work here. So you're going to have to stop and go, oop, wait a minute. Is that a composite function? If it's a composite function, I need to use the chain rule. Okay, that's what we're going to work on today. Okay, so one more of these. It's going to look a little bit different because they're not always radicals. Yeah, radicals. Okay, they're not always roots, square roots, cubed roots. Think about that one. Look at it and see, can you see a function inside of another function? Okay, if you can, then it's a composite. This guy is composite. Okay, so coming back here and I'm writing yes on all of these. Yes, yes, yes. This guy is composite. Okay, and I hope you all see it. And again, famous finger covering method, right? The outside function is something. Okay, so let me write it like this. The outside is something being cubed, right? Okay. If I just had x cubed, that would be awesome. We could take that derivative all day, 3x squared, and y'all would be like dancing in the streets if I put a million of those on the test, right? But that's not the way it's going to look, unfortunately. You'll probably have one of those, but not a million of those. Okay. So that is my outside function. Something is being cubed. Okay. On the inside of that, I also have a function, right? Does everybody see that? Is that guy a function? X to the 5th minus 2x? Yes, Dr. Webster. Okay, so my inside function is x to the 5th minus 2x. That's what's going on here. So indeed, I have two functions, right? One on the outside, one on the inside. Okay. And by the way, finger covering techniques are acceptable on tests. So if this works for you, for you to see the outside guy, the inside guy, then go for it. Okay. So those are my two functions, and I have an outside and I have an inside. And again, now that it looks like all this stuff inside of the cube, if it was just x cubed, it was an easy take, right? Okay, but once I have all this stuff, we're going to have to go a little bit more in depth and get a little bit more work going on. Okay, so here you go. All right, so let me just throw at you this general power rule that we haven't seen yet. It's going to look a lot like what you've already done, but there's one extra little added step. And if you've been following along and all the other sections on the taking the derivative stuff has been pretty straightforward, you're going to ace this. Don't worry about it. It's going to be good. Your biggest problem is in identifying, oh, look at that. That's a composite function. I need to take the chain rule. Okay, so here we go. General power rule. If u of x is differentiable, what does that mean? Differentiable. That means we can take the derivative, right? Okay. And n is any real number. It's going to be important for us because this is going to work on all the stuff we've been using, all the negative exponents, all the fraction exponents. Those are all real numbers. So when we get an exponent in here, it's going to work. Okay. The only thing it would not work on would be things that are not real numbers. What are those? Imaginary numbers. That would be like 2i. We're not going to have those in this class. You don't have to worry about it. If you were to take a Cal 2, a Cal 3 class, that kind of stuff, yeah, you'd have to worry about some of that stuff. But here we're not going to have that. So you're like, we don't have to worry about that, which is awesome. Okay. So you've got some function, it's derivative, you can take the derivative of it, and n is some real number. So just watch out for imaginary numbers. That's all we care about. Then y equals f of x equals, okay, be careful with this. U of x, that's the function, right? The inside guy, that's going to be my inside guy, raised to the n power, okay? So I didn't say when we did these earlier, but come back down here. I kind of said this guy, he could be written as raised to the third power, right? I didn't do it, but let's do it. Okay. The inside guy is x squared minus 1, and the power would be 1/3, right? Okay. The power is a 1. The root, it goes on top. The 3 is the root. It goes on bottom. Okay. We didn't do this one, but what's the index here? It's a square root, so this is a 2, right? So if I wanted to, I could rearrange this. 4 minus x squared, that's the inside guy, raised to the what power? The power is a 1, divided by the root is a 2. So is that some function raised to a real number? Yeah. Is this some function raised to a real number? Yeah. So what I'm saying is this chain rule here is going to work for this was some function raised to a real number. Yes. Okay. All these things that we're seeing that are composite functions, something inside of something else. Hey, look, we can write those like this as if they were a power. That's what we're saying here. So you're going to have your inside function. It's going to be raised to a power. Okay. So if all of that stuff is going on, that makes it what we're looking at here, then, then y prime equals f prime of x equals, and this is what we're going to do. It's going to look just like our power rule, okay? So we take this exponent, we multiply it out in front, n times u of x. What happens to the exponent? We subtract 1. So you guys have been doing this to the n minus 1. So that looks just like what we've been doing. So everything's just like what we've been doing. Sorry, I want to put this not in pink, n minus 1. Okay, so that looks just like the regular old power rule that we've been using, except we haven't addressed the fact that we've got more stuff going on the inside, right? So the last step is just going to say, oh, and take the derivative of the inside guy and multiply it. Okay. So once I finish, let's look at this. First, I deal with the exponent on the outside, right? Multiply it out in front. N minus 1 for the new exponent. Okay. So use your power rule just like you're used to. But once you've done that, don't forget, hey, I've got this function on the inside and I've got to do something with him. I can't ignore it. Unless that's just the x or just the whatever t or whatever the variable is. If I've got a function stuff, polynomial kind of thing going on, I'm going to have to come back here and multiply it by u prime of x. Okay. So the nice thing is, or the interesting thing is, actually for the power rule, we've already been doing this. Let me come back here one more time to the guy we just said, x to the 1/3. We've already been doing this, y equals. Okay. So y prime was multiply by the exponent, put your x, subtract 1, that's a negative 2/3. And then take a step back and look at this. If we said, hey, let's use the chain rule here. Okay. 1/3, subtract 1 from the exponent. We've done that. And then this would be my inside guy, right? Just the x. What's the derivative of x? Well, the exponent up there is a 1. You bring it down. 1 times x to the 0. What's x to the 0? That's a 1. 1 times 1 is 1. So what we should have been doing all along, I've just been shortcutting it, is we should have been looking at this guy x and saying, oh, and the derivative of x is a 1, so times 1. But why haven't I bothered with that? Why didn't we bother? Why doesn't the shortcut bother with that? Because anything times 1 what? Is just that thing. So we can ignore it when we just have an x inside, when it's not a more advanced formula in there or function in there. Okay, so that's what's been happening. We've actually just kind of been ignoring the times the derivative guy because we didn't need him. Okay, so that's what's up. I'm sorry, I didn't finish with my little rule here. Okay, so that was just a little example in the middle of that. So just to finish this out so that you know, um, I've got y prime up there, right? Yeah, y prime up there. I've got f prime up there, but also remember that that unusual notation. This is a much more mathy calculus notation, d dx or dy dx kind of thing. That is derivative notation. Take the derivative, and this says with respect to x. Okay, so dy dx of u to the n is n times, and it's the same thing, n times u to the n minus 1, but they've got this notation, du dx. What does that mean? The derivative of the u function, right? The derivative of the u function with respect to x. So that's what's going on there. And they've got a little note here. I just want to make sure everybody knows u equals u of x. That's here. They're just talking, they're being very mathy, very calculusy here, but it is in your book and it is in the homework. So if you see this dy dx kind of thing, d dx, du dx, any of that kind of stuff, that just means take the derivative. Okay. And if your function looks like a composite function, which you're going to be able to identify some of those, then yeah, it's going to be the chain rule. That's what's happening here. Okay. So I'll get you an actual definition for a chain rule for a second, but let's just kind of see if we can look at this general rule and see. So here's a couple of examples. So I've got an example and it says, you know that f of x equals 3x plus 1. Oops, I'm sorry. I guess it's 3x plus 4 now because I miswrote that. Let's say to the 7th power since I messed up. I said 1 and wrote 4. Okay, let's see what we can do here. Okay, everybody, before we go anywhere, does everybody see that the outside function is something raised to the 7th power? Let's see. We see that? What's going on the outside. And a lot of times there's parentheses. Sometimes it'll be, like I said, a bracket. Okay, but there will be some kind of a grouping symbol here that kind of helps us see it. Okay, the outside function is we're raising something to the 7th power. That's on the outside. But the inside function, so I'd really kind of like for you to take this it's not going to take forever, just a couple of seconds, and identify the difference between the two of them. What's on the inside? 3x plus 4. Yeah, that's what I heard too. Okay. So on the inside, I've got 3x plus 4. On the outside, I've got it being raised to the 7th power. Okay. So we're going to take the derivative using this general power rule, okay, that we just saw. F prime of x equals, and it looks just like what we've been doing before. So the very first of it looks exactly the same. Take your 7, multiply it out in front. 3x plus 4 raised to the what happens up here? 7 minus 1 is 6, right? So all of that, if you can't remember the chain rule, you better at least get that far because we've been doing this for 2 weeks now, right? Okay, so we've been doing this power rule thing, and you should be able to do that by now, even if the chain rule bit throws us. But hopefully it doesn't, because now we're done with the outside function, right? We took the derivative of the outside function. Now we need to, this was it. Now we need to, so ignore that. You're done with that. That's the derivative of the outside function. Now we need to take the derivative of the inside function. Well, the inside function is 3x plus 4, right? That's what we said. Okay. What's the derivative of that? This is x to the first. Work through that on your own for just a second if you need to. 1 times 3 is 3. X to the 0, right? Because I'd subtract a 1. Okay. What's x to the 0 going to be? Anything to the 0 power is a 1, right? So that's going to be 3 times 1. And what about that 4 sitting out there? When we take the derivative of the 4, the derivative of any constant is 0, right? So you could put plus 0 out there, but again, we don't need it. We don't need the 1. We don't need the 0. Okay, so this just ends up being the derivative of the outside function times a 3. Okay, now you can clean that up just a tiny bit. And what I find is from here on out, the rest of all this calculus stuff, people struggle with cleaning it up. Okay, they struggle with the algebra part of this. That's all the calculus is. We're done with the calculus. Okay, so don't let the calculus stress you out. You've already been doing this for a while. So we've got the cleanup work here is a 3 times this whole thing. Well, I'm not going to multiply 3 into this thing to the 6th power. Nobody's going to take the time, or at least I hope you don't, to go 3x plus 4 times 3x plus 4. What does that mean? 3x plus 4 times to the 6th. Times itself 6 times, right? I'm going to write this one out. I'm never going to do it for you again. Okay. 3x plus 4 times itself 6 times. That's what 3x plus 4 to the 6th power means, right? And is anybody going to sit around and multiply all that junk out to find out what that is, just so you can multiply that 7 and that 3 through? Lord, I hope not. That's a waste of our time. Okay. So we're not going to do that. Instead, we're just going to say, hey, these two numbers on the outside, that's a 3 times a 7. That's a 21. I can deal with that, right? I can multiply those because it's all being multiplied. And when you're multiplying, order doesn't matter, right? So I can rearrange this. 3 times 7 is 21. And then I'm going to leave 3x plus 4 raised to the 6th power alone. Okay. Don't mess with it. We're not going to do this. If you do this on a test, you will not have enough time to finish your test. Okay. So don't do that. It's not worth it. We're not going to do that. Okay. So we're just going to rearrange, clean up. That's what I call it. Clean up some of that math stuff. Now, sometimes we might have 3 times, I don't know, x plus 1 out here in parentheses. Well, 3 times x plus 1, that's easy. You should clean that up, right? But this 3x plus 4 to the 6th power, no. And in fact, somebody told me not too long ago, it was another teacher, that on their test, and I'm thinking about doing this for you guys, I'm just letting you know. Here's another example. She said on her test, what she does is she makes the exponent so big that nobody would bother trying to take the derivative of it or multiply it out. So say I make this a 400 or something. That looks a little intimidating, right? But it's not really. Okay. It shouldn't be any more intimidating than the 7 was. So we can do this because why she said she does that is because that way you're not tempted to do this. No, I really don't think anybody's going to multiply x squared plus 11 times itself 400 times. Please don't do that. We would never ask you to do that on the test. If you saw something like that and you went, oh my gosh, I'm going to be working on this for 2 hours, then that means there's a shortcut, guys. Okay. Don't do that. You're taking up way too much of your precious testing time, right? Okay. So let's look at this. F prime of x. Oops, let me come off to the side. I'm sorry. Do you see the outside function? Do you see the inside function? What do you think the outside function is? I think it's something being raised to the 400 power, right? Like ignore the stuff inside the parentheses. Something being raised to the a 400th power. I don't think I said 100. Okay. Okay. And then if you ignore the 400, what's the inside function? Well, that one's pretty easy too, right? Excuse me, x squared plus 11. And you don't have to come out here to the side and do this, but if you're getting confused and you like need to take a step back for just a minute, then do this. It didn't take me but a few seconds to write these two functions out. Here's my outside guy, here's my inside guy. And then we do this. Let's deal with the derivative of the outside. So take this 400, we're going to multiply it out in front. 400 times the stuff in the parentheses. We don't care what it is, just write it down. And then what happens to the exponent? Subtract 1. Oh, I'm sorry. I went the other way. So 400 minus 1 is 399. It would help if I could do basic arithmetic. Okay, don't know why I was trying to add. Okay, so 399, that's the derivative of the outside function. Does everybody agree? Like if this was an x, I would have said 400 subtract 1, and I'd have 400x to the 399. Okay. In this case, instead of an x, it's kind of like substitution. Remember when we did substitution, when we were doing difference quotient? It's kind of like that. Instead of an x, I'm just sticking that in there. I don't do anything to it right now. Okay. It's just like along for the ride. He just stays in there. All the stuff raised to the 399. I'll deal with him in a second because what's the next step that we're going to do? We took the derivative of the outside stuff here. Now I'm going to take the derivative of the inside stuff. What's the derivative? I'm going to write it right here. The derivative of the inside. Ignore this right here. What's the derivative of the inside? Here's the inside. Well, that's a power rule, right? So that's just 2x. And what's the derivative of the 11? It's a constant, so it's 0. So that would be 2x plus 0, but we don't care about the 0. So what's the derivative of the inside? 2x, right? So times 2x. Excuse me. All right, that's it. That's the calculus. We're done with the calculus. Now is the cleanup. Don't forget the cleanup. You need to take a second and go do your cleanup. So go do it. I'm going to push pause. Okay, hopefully you pushed pause and you dealt with that. What do you think the cleanup part is? I think there's a 400 being multiplied and there's a 2x being multiplied. So I think you can rearrange this. 400 times 2x is going to be 800x. And then all this stuff in the parentheses, just leave it alone. We are not going to multiply or mess with some stuff that, well, being multiplied by itself 399 times, right? We're just not going to do that. Okay. So don't stress out about that. We're not going to deal with it. We're not going to do anything. Okay. All right. Let's do one a tiny step more. I don't want to say harder. It's just more. More for you to think about, more for you to say, hey, is that really a composite function? So here we go. Your example, and I don't know why, but the book changes to h of w. Okay, h of w equals the square root of 3 minus w. Okay, so look at that guy. Do you think it's composite? I do. What's my outside function? I think that on the outside, I have that square root, right? A radical. The index is a 2 because there's nothing written there, so it's automatically a 2. And I think on the inside, if I ignore the bracket, I've got what? 3 minus w, right? Okay. So, before I go to do any derivative type stuff, I'm going to rewrite this, right? Because we don't like it the way it looks. It's got that radical. So, let's rewrite it. H of W equals, this power is a 1, this root is a 2. So hopefully you're pretty fast at this by now. You can say 3 minus W, because that's all the stuff in the brackets, right? To the 1 over 2. Here's your power, here's your root. Power, root, flower, power. Okay, so remember that. Here's your flower. There's a stem. I can't remember if I made this drawing for y'all or not. Okay, there's the roots. My power is up here. That's what everybody cares about with the flower, right? Is the petals. There's where the power is. But the roots are way down here. So when you write it as a fraction, it's power over roots. So flower power. I know. If it's goofy and you don't like it, then just ignore it and figure out a way to remember that. I think I did that because I think I remember saying exactly what I just said. If this doesn't make sense to you, or if it's just confusing, or you don't like it, or you think it feels silly, then don't worry about it. Figure out your own way of remembering that it's this number, the exponent, 1 over this number, the index, the root, 2. But if you're kind of a visual person, the power on the top, the roots on the bottom, hopefully that helps you with those changing radicals into fractions, fraction exponents. Okay, anyway, this is 3 minus w raised to the 1/2. What's going on with this guy? How do I take the derivative? So h prime of w equals, multiply that in front. It's a fraction, but we don't care. It'll be okay. 1/2 times, write down all the stuff in the inside. We don't care about it. It's the inside function. We'll deal with him in a minute, right? So we're dealing with the outside function first, the 1/2, and then we're going to subtract 1 from the exponent. So what's 1/2 minus 1? Negative 1/2, right? Okay, so that's the outside. We multiplied. We've got the stuff. Just rewrite it. Drag it along for the ride. That's what I like to say. And then subtract 1 from the exponent. Okay, and then we need to take the derivative of the inside function. Be careful with this one because whenever we go to take the derivative of the inside here, people get confused because the minus w there. Okay, so the derivative of 3 is just 0, right? And the derivative of constant is 0. So that goes away. We don't care about that. But remember, the exponent on this w is a 1. So when I go to take this derivative, it's 1 times negative 1 is negative 1 w. What happens here whenever I go 1 minus 1? 1 minus 1 is 0, right? Oh, that's that guy. 1 to the w to the 0 is a 1 power. No, I'm sorry. W to the 0 power is a 1. So what's negative 1 times 1? Negative 1. Okay. So if you need to do that math out to the side, do it just like I did there. If you can do it staring right here and go, oh, that 3 is a 0. What goes on with this? It's a negative 1. However you can do that. That's all the calculus. Okay. You just got to figure out what to do with the inside guy. Take his derivative. His derivative is negative 1, and we're going to multiply by that. Okay. That's the new rule that we're working with. Okay. And then we need to clean it up. We've got a 1/2 being multiplied by a negative 1. So that's negative 1/2. And then all this stuff with the parentheses stays the same. Don't forget your negative 1/2 on the exponent. I'm kind of out of space here. I'm sorry. Okay. So negative 1/2 out in front because I multiplied these two things together. 3 minus w, because that's all the stuff inside. I like to say stuff or thing. Okay, the inside guy, that's the inside guy. He's just coming along. Raised to the negative 1/2 power. All right. Okay. Um, let's try kind of a weird one. Yeah. This one's a little bit more. So again, they just start getting just a little bit more and a little bit more. You can handle it. It's kind of on a test. I generally start out with a kind of simple example of whatever rule we're trying to work with, and then I work you to the more difficult stuff, right? So, um, this one says find dy dt. Okay, so when you see that, you're going to go, oh, that's derivative notation, right? If y equals, and it's 1 over parentheses, t squared plus t plus 4 raised to the third power. All right. So, this is another one of those that I'm going to look at it and go, ooh, I don't want to deal with that as a quotient rule if I don't have to. And I really don't want to deal with this one as a quotient rule because he's a composite function inside of a quotient rule. Do you see that? You see the outside function is the 3 and the inside function is that polynomial there, t squared plus t plus 4. So I know already I've got a composite function. That's a chain rule, and it's inside of a quotient rule. I don't want to deal with that. So what I want to do and what I kind of encourage you to do, because power rule is a lot easier than quotient rule, right? There's just more steps in quotient rule, is I want you to take just 2 seconds and rewrite this. Okay, we can rewrite this. How do you think I want you to rewrite it? Okay. I'm hoping that by now, when you see something raised to a power in the denominator, in your head, you recognize, oh, that's in the denominator. I can move it to the top if I do what? And put this whole thing on top if I change the sign on that exponent, right? That's one of our exponent rules. So I'm not taking the derivative. I am just rearranging this. Y equals, there's a 1 on top, so we don't really care about multiplying by 1. This whole thing, t squared plus t plus 4 raised to the, if I put it on top, the 3 becomes -3. Okay. How much easier is that going to be to take this as a power rule? Right? Because we love our power rule. Okay. So if we can do the power rule, our little shortcut, that's a lot easier than doing the quotient rule. Remember the quotient rule, low-de high, high-de low, low, low? Yeah, that's a lot, right? I can do this as a power rule, and that's how I would like to do it. Okay. So rewrite it first. Take that. It didn't take me but just a couple of seconds. And then we can take the derivative. Okay. So I'm going to come over here. Does everybody see the way I have it? My outside function is something raised to the -3. Okay. All this stuff raised to the -3. And we know that we can multiply that -3 out in front and subtract 1, which is what we're going to do. Okay. And then my inside function here is t squared plus t plus 4, right? That's what's going on inside of the parentheses. All right. So let's do it. Multiply the -3 out in front. T squared plus t plus 4. Subtract 1 from a negative number. -3 minus 1 is -4. So be careful with your arithmetic there. We did that whenever we did power rule, right? -3 minus 1. That's it for the outside function, right? Multiply here, subtract 1, make sure you go in the right direction with your subtraction. We took the derivative of the outside guy, right? So now I'm done with this stuff. Okay. I want to take the derivative of the inside function. Well, here was my inside function. The derivative of the inside function is just what? Well, that's a product or a polynomial. So this is 2t. 2 minus 1 is 1. I don't care about that guy. Plus, this has a 1 up here. 1t to the 0. T to the 0 is a 1. 1 times 1 is 1. Plus, what's this guy? 0, right? So we don't care about that. So this is just 2t plus 1, but it is a binomial, right? This is the first time I've had that. So I need to put it in parentheses because it's this entire thing being multiplied, right? Multiply that entire thing. That's what we're doing. So when you do that, you need to put parentheses. All right. Now, again, am I going to try to distribute into this guy with the -4 power? No, we're not doing that. Don't waste your time with that. But the -3 and the 2t plus 1, can we multiply that? Yes, we can. Let me rearrange it real quickly. Y equals, I've got a -3 times a 2t plus 1 times all this stuff, t squared plus t plus 4 to the -4th. My allergies are bugging me. I'm sorry, guys. To the -4th. Okay. So, but again, I'm not messing with this stuff inside. That's a T. This is a plus. I'm sorry. Okay. So I didn't change that. It's the same thing that's right here. Okay. I just got all run together. I'm sorry. Okay. So I'm not messing with this guy. Raising something to the -4th power, yuck. If you want to, you can put him back on bottom, right? Because he's got a negative exponent. He came from the bottom. That's how he got the negative exponent. So if you wanted to move him back down to the bottom, you can. And I'll show you what that looks like in a minute. Okay. But first, I want to clean this up. We can do this. Everybody in this classroom, everybody who's listening to this video can do this. So that's just distributive, right? Okay. -3 times 2t, that's -6t. -3 times +1, that's a -3. Okay, this is still a binomial being multiplied by all this stuff. So I still need parentheses on it, is my point. Okay, but I can distribute that -3 through. That's what I get. That's how it cleans up. And we're done. Okay. If you really wanted to leave it right here, you'd be okay. I wouldn't thrash you on a test for that. But as much as you can clean something up, I would like for you to clean something up. Okay. So I'm perfectly okay with this, and you can stop right there. However, some teachers don't like these negative exponents, and occasionally I've seen in my math lab where it'll say, don't leave a negative exponent. Okay. So let me show you how we rearrange that. But for my purposes on a test, I say stop right there because if you do more steps, you're likely to make a mistake. And I don't want you making mistakes for something that I don't care about, right? But this guy has a positive exponent. It's +1, right? So he stays on top. -6t minus 3, he stays on top. This guy has a negative exponent, so I can move that whole thing to the bottom. T squared plus t plus 4. And when I move the whole thing that's being raised to that power to the bottom, the -4 becomes a +4, right? Okay. So if you are like, I hate those negative exponents, or if my math lab is being kind of stubborn and doesn't want negative exponents or something like that, you can do that. All right. Just be aware that's possible. All right. That's kind of one of the more difficult ones, I would say. More stuff, more advanced, more stuff going on with it. But I feel like everybody should be able to do this, especially if you're good with those exponent rules that I've been begging you for weeks now to make sure you know how to do your exponents rules, right? So, all right, let's get the chain rule officially. The chain rule looks like this. Okay, so that last one was the general power rule, and we were just trying to say, hey, can we use that? And absolutely, the chain rule is just a very specific part of this. Okay, and I'm just going to use the notation in the book. They say if m of x, it's an m, 3 humps, equals the e, which they call the exterior guy, of I of x. See how that is composite? This function is inside of that function. The inside function is inside the x outside function. Okay. If this is a composite function. Okay. The inside guy and the outside guy. then m prime of x equals, take the derivative of the outside function, leave the inside guy in there, okay? All the stuff stays on the inside. I think that's the thing that people struggle with the most. Just write the stuff, okay? Don't worry about it. The stuff is going to be there on the inside. Okay, so the x, take the derivative of the outside function. They're calling it a for exterior. I like outside, but you can call it whatever you want. Okay, so take the derivative of the outside function, keep the guy inside, just along for the ride, times the derivative of the inside function. Okay. Doesn't that sound like what we've been doing? The derivative of the outside function times the derivative of the inside function. All right. So I'm going to give you, let's see. Let's do 2 examples. I'm going to put them up here, give them for you to work on, and then you push pause on the video and go see what you can do with them. Okay. They're both going to be some application of this chain rule. Okay. One says g of x equals parentheses 3x squared plus 1 raised to the 3 halves. Okay. Find g prime. It should be an if. Okay, if g of x is that guy, then find g prime of x. Okay. Do you think it's a composite? Does it look like a composite function? Take just a second. Can you see the outside function? Can you see the inside function? Okay. If you need to write those out to the side, write them out to the side. But it looks like a composite function to me, so you should be able to use chain rule. Okay, so there's one. And then the other one is if f of x equals 2x to the third plus 4 to the negative 5, then find f prime of x. Okay. So I feel like you should be able to run through these 2 pretty quickly. They definitely look like power rules to me. I'm going to press pause and do my work. You press pause and do your work. And when you're ready, come back and see if your stuff matches. All right. I feel like I've got them. I hope that I didn't make any crazy arithmetic mistakes. Okay. But here on the first one, I multiplied by 3 halves out in front. I subtracted 1 off. Be careful because 3 halves minus 1 is 2 halves, right? 3 halves minus 2 halves is 1 half. So it's still positive here. That's a fraction bigger than 1. So when I subtract 1 from it, I still get a positive 1 half. And then the derivative of the inside function, it's really just the derivative of 3x squared, right? Which I think is 6x. Okay. Then I multiplied 6x by 3 over 2. I got 9x because 6 times 3 is 18, divided by 2 is 9. And then all that stuff, I just rewrote it with the 1/2 power. Okay. Hopefully that looks like something you did. Take a second to work on your stuff or look through and figure out if you made a mistake. I'm pretty sure that that's correct. Do I have the answers? No, of course I didn't write them down. All right, so I'm pretty sure that's right. Okay, and then I've got this guy, same deal, except for I've got a negative integer up here. So when I pull it down, I multiply by -5 out in front. -5 minus 1 is -6. So be careful with that, right? That's the only difference is now I've got a negative minus a number that's a negative. Okay. All the stuff inside the inside function, notice he's just sitting there, right? He just comes along, he stays on the inside, multiply with a -5, subtract 1 from the exponent, but the stuff inside, leave him alone. I promise you that's where a lot of people struggle. They want to do something to that. Don't do anything to the inside until you get finished with the outside. So take that guy's derivative of the outside, times then take the derivative of the inside. Well, the derivative of the inside, again, the 4 is going to be a constant, right? So that's 0. So what's the derivative of 2x to the third? It's 6x squared, right? 6x squared. So then I just said, well, I've got a negative 5 being multiplied. I've got a 6x squared being multiplied. Negative 5 times 6x squared, that's negative 30x squared. All right. I think so. All right. All that stuff's just along for the ride with that negative exponent on it. Everybody okay? All right, I got 2 more, and then if I were you, I'd go play or take your quiz and then play with your homework and see how it goes. So again, I feel like you should be able to work some of these on your own. Next example is if f of x equals 4x to the 5th minus 3x to the 3rd plus 4x plus 10 raised to the 7th power. It looks kind of big. Yeah, we can deal with it. Then find f prime of x. Okay. Again, go ahead and take a look. Does this look like an outside function? Something's being raised to the 7th power. Yep. This looks like an inside function. This is composite. Hey, I think I need to take the chain rule. That's literally what happens in my brain, guys. Okay, so I literally do that. Oh, look, there's this big polynomial and it's being raised to a power. That's an inside function and an outside function. That's composite. I'm going to use chain rule. So if you want to work it on your own, you can push pause. I'm just going to start working it. So it's going to be, you can come back and unpause me in a second and listen to me if you want to. But I say 7 on the multiply by the 7, leave the stuff on the inside as it is. So just write it all down. 4x to the 5th minus 3x cubed plus 4x plus 7. And then I need to subtract 1 from the 7. So that's a 6. Okay. That's the derivative of the outside guy. Okay. Now we're done with that. The only thing left is times. I need to take the derivative of the inside function. Now this guy is definitely going to be a polynomial. So I need to put parentheses. And then let's walk through this one at a time, one term at a time. The nice thing is these are just power rules, right? So 20x to the 4th when I subtract 1 there. 3 times negative 3 is negative 9. X to the 3 minus 1 is 2, right? This is going to be a 1 minus 1. That's going to be x to the 0, so it's just a 1. So this is going to be plus 4. And the last guy here is a 10. That's constant. His derivative is 0, right? So we just ignore those constants because we know they're going to drop out. Okay, so this is what I meant by, hey, that's a big polynomial there in the derivative. So sometimes we might have a longer polynomial and this started with 4 terms. Now we have 3 terms in our derivative. That's fine. We don't care. We can deal with it. Okay. Just remember to put parentheses because they're all being multiplied, right? And then I see one little step of cleanup. If you want to, you can write these, you can rearrange them. They're all being multiplied, which means the order doesn't matter. So I think I'm going to write them like this. Okay, the 7 being multiplied by that 20x to the 4th minus 9x squared plus 4. And then that big 4x to the 5th guy, all of that stuff minus 3x to the 3rd plus 4x plus 10 to the 6th, all of him by himself. This one's getting big enough. I mean, I would probably go ahead and multiply him through, but again, if you left it just like that, I'm probably not going to argue with you or make a fuss on a test. Just for my purposes, I'm going to go ahead and multiply this 7. I'm going to distribute it into this first set of parentheses, right? They're all being multiplied, so I only have to multiply them once. So it's easier for me to multiply them into the first set of parentheses. I'm not doing anything with that guy, right? It's 4 terms times himself 6 times. Don't do it, guys. Leave it alone. Don't torture yourselves. But this thing I can make it a little prettier. 7 times 20, 140, x to the 4th. 7 times negative 9, I think that's negative 63 x squared. 7 times 4 is a positive 28. It's all of that still being multiplied. So I need the parentheses. Don't drop your parentheses. It's things like dropping your parentheses, those little mistakes that'll totally mix it up. Because if I don't have parentheses here, then all I'm saying is multiply the 28 through, right? I don't want just the 28. I want all of that multiplied through. So put parentheses. Be careful with your notation. All right. And our last one, and again, you want to pause it so you can work on it. You should do that if f of x, let's say g of x, just because I'm tired of f's. If g of x equals the fourth root of 3x to the fourth minus x, then find g prime of x. Okay. This one, I will say before you press pause, you need to rewrite this guy, right? Because he's a radical. So again, rewriting is not taking the derivative. This is the same thing. I'm just making it look a little different. So when I rewrite it, all this stuff on the inside is going to be raised to the what? What's the exponent? A 1. And what's the root? A 4. So you're going to raise this whole thing to the 1/4 power. Again, that's not a derivative. That's an algebra. That's an exponent rule. Okay. So that's the stuff I've been asking you to make sure you know those exponent rules. We did that exponent review. Hopefully you did it and hopefully you understand all that stuff, because that's going to be, for some of you, your big mistake is you don't know what to do with those exponents. Okay. You don't know how, if you don't know how to change this guy out of a radical into that fraction exponent pretty fast, then you're just going to hurt yourself on the test. Okay. Because I promise you, I don't always make promises, but I promise you there will be something with a radical on test 2 on this exam that you need to deal with, making that radical into a fractional exponent. Okay. And that's not derivatives. That's just dealing with your exponents. Okay. Now let's take our derivative. G prime of x equals, if you want to pause and do it on your own and then come back, you can. 1/4 on the outside. Leave the stuff on the inside alone. It looks just like it did above. 1/4 minus 1 is a negative 3/4. Be careful with this fraction minus 1. And then, so that's all the derivative of the outside, right? Then if you need to cover that up, cover it up. The derivative of the inside, be careful with this guy. 3x to the fourth, that's going to be multiply 12x to the third when I subtract 1, right? 12x to the third. And then this guy is minus x, so it's going to be, that's a 1 up there. Minus 1, x to the 1 minus 1 is 0. Okay, x to the 0 is 1. Negative 1 times 1 is 1, right? So all that stuff just becomes, the derivative of it is 12x to the third minus 1. Okay, because this is just a 1. Can make it a little bit prettier by rearranging. G prime equals 1/4 times 12x to the third minus minus a 1. See, that's why I just say it's a 1. Okay, and then times that 3x to the fourth stuff. 3x to the fourth minus x to the negative 3/4. On this one, again, I'm okay if you leave it just like this. It's not too terrible to multiply that 1/4 through this first set of parentheses, but you are going to get a fraction in there. So some of you that might stress you out. 1/4 times 12 is a 3x to the third. Okay, distributing, putting this 1/4 through, right? Okay, 3x to the third, but 1/4 times a negative 1 is a negative 1/4. That's why I meant you're going to get a fraction. And then this rest of this stuff is just sticking around, 3x to the fourth minus x to the negative 3/4. I will accept either one of those. Okay. But the second one is definitely the cleaner version. And I have had students in the past who really didn't like this negative here. So if you realized, oh, that negative, I can move it to the bottom and make it a positive exponent, you can absolutely do that. And in fact, you can move it to the bottom and make it back into a radical if you want to. I'm not going to do that because I don't think it's worth it. It's a lot of places where people might make a mistake, and I don't want you to take that chance. All right. That's it for the chain rule. Those are all your examples. I think you should be good to go on doing your homework, and let me know if you have questions. Thanks.